Yes, we are live on YouTube as well as on Zoom. Good evening, participants. Welcome to the live session of the course Metallurgical and Electronic Waste Recycling. Our instructor, Professor Arunabh Meshram sir, is here with us along with our teaching assistant, Ms. Neha. Kindly join in and please feel free to ask your doubts. Over to you, sir.
Yes. So, I welcome everybody for this. Yeah, yeah. All right. So, some of the questions that have been put up, we'll just try to look at those questions and see if we can really answer these good questions. So, one of the key questions that I find really interesting is can you explain with an example how unit operations are interconnected in a typically recycling process? Unit processes are interconnected. Yes. So we can't really have a recycling process in isolation. So, for instance, if you look at, um, let's say, uh, pyrometallurgical route or hydrometallurgical route or electrometallurgical route, we don't really do these recycling processes in isolation. They are always done in connection with one another, and same is the case with pre-treatments also. So the unit operations are sort of interbranched in the sense that you can have multiple unit processes following one after the other or in loop so as to achieve your desired results. And then you get your basically final product, which is the raw material for the recycling. So how do we really put one unit process after the other? And how is one unit operation interconnected with the next? So let us look at, let's say, an example of, let's say, recycling of batteries or recycling of any common electronic waste or any common metallurgical waste. Now, this waste, when we reach this waste, when this waste really comes to us, so somebody has to carry it to us, or rather, we go to this waste. Either ways, if there is logistics involved. First, second, one has to really carry this waste to the unit operation unit, the place where we are going to, well, say, let's say, start our pre-treatment. We want to do crushing, grinding, sieving, or you might want to do, let's say, there is something in the orders of, let's say, froth flotation, gravity separations, tabling, jigging, and all of these unit operations. One has to really plan how we are going to move about from, let's say, just reducing particle size to separating out various particles of different phases physically. And if we really want to do some more thermal treatment, chemical treatment, what would we want to do? So in that sense, your unit operations are generally interconnected. One of the most important USPs of pre-treatment, unique selling propositions, USPs, so is that we don't really focus on one particular type of unit operation and say that this is it. Unit operations tend to give us wide variety of properties of the products and properties. But we need to choose the unit operations wisely. So suppose that there is a material that contains some phases that are receptive to magnetic field or electric field, or let's say they are more responsive to uh, optical lights. So based on that, this specific property, we can try to identify what really uh, is the constituent of our raw material. And then maybe we can sort of sort it or collect it or separate it, and then we can do the further processes. Now, in that sense, unit processes are interconnected. Sorting itself would require you to sort based on some properties, right? It has to be either magnetic properties, optical properties. You can take pictures. You can also have X-ray exposure and check whether a given material has some properties related to that or not. And based on such properties, we can sort of sort. So just based on sorting, which is again a starting step, we can see that it is so much interconnected. So of course, there are so many unit processes and unit operations that have been lined up in most of the recycling case studies that we cover in this course. And these are essentially interconnected, because one property is being exploited to get a product which is the starting material for the next operation. So suppose that you want to do leaching, you need fine particles. So for fine particles, we need, let's say, pre-treated, roasted, or something else, or some specific type of fine particles. So that contains very specific types of chemical products. Let's say it should contain some oxides, let's say A2O3, ZNO, or something of that sort. So one should really think, okay, fine, let's just oxidize our raw material and then see how it reacts with let's say H2SO4 or NaOH or any other leaching reagent. So that type of recycling comes only when you have a very good pre-treatment, and then you need really good unit operations that are sort of interconnected before the actual recycling starts. Well, the second question is basically how among different waste classifications, which category is most challenging for metallurgical recycling and why? Well, uh, essentially speaking, almost all of these waste categories are challenging, and the challenges are different for every segment itself. So, say if you try to look at solid wastes versus liquid wastes versus gaseous waste. So all of these categories are altogether different. And based on metallurgical waste, which we are trying to classify in terms of elements, there could be classification based on the process itself, let's say pyrometallurgical process, electrometallurgical process, or hydrometallurgical process. So in that sense, all of these classifications really get dissolved. So challenges are there in any category that we look at, and we can just sort of take an example for to just understand what we really mean. So, for instance, if you look at uh, leach liquor waste, which we may now call as raffinate also. Leach liquor waste, because you've extracted most of the metals and metallic values from it by some way or the other. There is solvent extraction, ion exchange, electrowinning, precipitation, co-precipitation, there is polymer inclusion membranes, there are liquid membrane extraction. There are so many different new categories of metal recoveries that are coming up. So if you look at spent spent leach liquor, let's say, what do we do with it? Which is also part of a question which is being asked in the question series. So what do we do with these types of wastes? The answer is we really have to understand what is the volume of the waste that we're looking at, and can we reuse it by some chemical composition at this point? Because we are looking at a waste at an industry, and industrial waste generally are very large in volumes. Can we do some sort of chemical treatment to make it reusable? If yes, that's great. If no, then can we utilize this for some other purpose altogether? Let's say you want to use this leach liquor, which contains so many ions, into some other uh, for some other applications that may use these ions for making some valuable materials. So that is a challenge, and it totally shifts for every category of waste. Every category within every element, or every category within every process route. Let's say pyro route, hydrometallurgical route, electrometallurgical route. It changes. So in that sense, all wastes have their own very specific problems, and it is sort of very difficult to really say, okay, this type of waste will be most challenging and the other will not, because when we look at metallurgical waste and electronic waste, all of these wastes generally have some or the other component that could be environmentally hazardous, or is economical to require one or the other element. So when we are faced with multiple process optimization challenges, it becomes very difficult to let go of some element because, let's say, it is not so economical, or it is or we sort of are overlooking environmental constraints. So in my opinion, all of the waste should be treated with utmost care, so that the classifications and the processes that are involved in recycling are very well understood, and they are addressed properly. The challenges are addressed properly, so that the 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 recycling is properly taken care of. Now, next question is, in zinc dross recycling, how do we ensure purity levels suitable for reuse in galvanizing operations? Now, zinc dross recycling would require you to sort of go into various routes that we have already discussed in the video lectures. Let's say you want to, based on what type of work that we are trying to do, we can do pyrometallurgy, hydrometallurgy, combine it with other routes, also pre-treatments as well. But when we think about purity levels, we really need to make it refined, in the refined state. So refining of zinc would be the end target if we really want to bring it back for galvanizing. Of course, there are multiple ways of recovering zinc the metal, not zinc products. But if you want to make zinc the metal, then you'd like to preferably want to go into, let's say, pyrometallurgy, if not hydroelectro. Then your products have to be refined in either of the cases. So just achieving recycling step and recovering zinc the metal is not the end goal. For most of the metallic recoveries, it is highly recommended that refining is associated after the recycling step. So that would be very important. The next question is, why is raffinate considered a critical stream in copper recycling, and what are the main challenges in handling it? So, critical stream in copper recycling. Now, so just a similar example we've just taken. Say, if you're looking at raffinate is essentially the liquor that is left after leaching, and you recover materials from it, and you're left with some ions left inside it, and majority of your target metal is essentially taken away. So theoretically, it should have very less amount of, in this case, it is copper. So theoretically, you should have lesser amount of copper. That really doesn't mean that there is no copper at all. Some amount of copper is always present in refined solutions. So yes, it is sort of important to not let go of the uh, raffinate streams. But at the same times, why is it so challenging? If it is so important, why just not recycle it directly? The term raffinate comes only after you are reusing your leach liquor multiple times. And it so happens that the amount of ions that can be present in a given volume of raffinate could be saturated. So in that sense, now the solution sort of becomes not so usable for, let's say, let us put it back as a solution for leaching. So that may not be the desired way of handling your raffinates. So what do we do with it? One common method is that let us tap the ions from the raffinate and try to make some valuable products. That's a very common method, which is being explored in labs and is being tried in various industries also. What they can do is, if they can somehow change the pH, if they can change, if by addition of some other chemical reagents, some materials can be precipitated and these materials can be refined. Again, refining is a critical step. You make a product, you refine it. So when you go for fabrication of valuable materials or products from these spent raffinates, or let's say electrolytes, I think that spent electrolyte is also being asked. So when we look at these types of liquid wastes, the target has always been to recover some metallic values by precipitation, or let's say electrowinning, or some, let's say, cementation or some other route, so that you get your product and then you refine it and then it becomes marketable. What are the main challenges? Of course, the quantity itself and handling of the raffinate solution volumes, that is a very big challenge. And it's always a lot more easier to conduct some experiments here and there in a lab scale, but to really scale it to a large level with large working volumes, we need infrastructure. And the most important aspect that I have always discussed, the logistics of the raw materials, the way by which one material will be carried from one spot to the other, that has always been a challenge. And the way various materials would be mixed. Let's say you want to add a given material into something else, and then some other product is supposed to come out. That would come out only when you have proper mixing. And you want to do simple precipitation. So one material has to precipitate out by your addition of, let's say, some material X. Now, if Y is supposed to come out, you have to add X and assume that your X is going to react with your raffinate or spent leach liquor, or let's say spent electrolyte, or whatever fluid that is. It has to react. If it doesn't react, then of course it's no point in addition. Now, when we think about mixing, the most important challenge has always been to really think whether a given raw material would be completely be able to react with it or not. So there is the challenge of addition and achieve and thinking whether this will completely react or not. So these are some important challenges that we can really consider. Logistics, material handling, energy balances, and of course, process efficiency. Now, how do we manage the balance between metal recovery and impurity removal in copper scrap recycling? Metal recovery and impurity removal, that has to do with pyrometallurgical optimization. Now, generally, most of the scraps that we see from various metal industries, they've always been dealt with generally by pyrometallurgical route. Very few cases would be observed or seen where you are using a given metal scrap metals. I'm talking about scrap metals, which would require you to go into, let's say, hydrometallurgy or hydroelectro or some other route. The most common method is take the scrap, process it, maybe clean it, degrease it if it is, because we are looking at a scrap, it is of course going to contain some dirt or grease or something like that, and then we just need to bring it to the pyrometallurgical unit, which could be a smelter or a remelting unit, and then process it there, and then you can grab your metal in the form of molten metal and then cast it. How do we manage the metal recovery? That has to do with the pyrometallurgical process that is being done. If there is refining required, you do it there. There, of course, you would be requiring some slag that helps us in refining the impurities that are present in the copper, and these impurities they may get distributed into the slag phase, and then you can recover the slag phase by casting the metal, and you treat this copper smelter slag, which again is which has been covered in the course. So that is how you recover copper from your copper scrap. How could you explain? Could you explain how spent electrolyte from copper is treated to minimize waste generation? Uh, well, there is some clarification that would be required in this question. Copper smelters do not generally produce spent electrolytes. Spent electrolytes would be coming from, let's say, electrolytic units and not essentially copper smelters. So smelting is basically a pyrometallurgical unit, and electrolytes are generally coming from electrolytic systems, which are electrometallurgical in nature. So in that sense, I'll try to answer from the spent electrolyte perspective. Spent electrolyte, I've already said, is like is a liquid which would require you to collect the liquid. If it is not usable, you collect the liquid, check the ionic composition, check how we can recover, let's say, acids or some other valuable materials, and see if we can add something into it and recover something valuable. That would again depend upon the elemental composition of the waste. So in this case, it is copper. We assume that some amount of copper would also be there, even though generally speaking, it would be very less in quantity, but still it would be present in some quantity nevertheless. Now, the next question is, in hydrometallurgy, how do we handle the issue of large amounts of effluents generated? This is something similar to what we just discussed. Liquids and gases, the fluids that are generated, it's always been a major issue. The common practice is to sort of neutralize it before we are, let's say, discharging it. And as I've just mentioned, we just try to recover something valuable from it based on the composition. Direct disposal is, of course, not feasible, and it is not recommended. So that is always been a challenge. The large quantities of fluids, effluents, let's say each liquor, or let's say spent electrolytes, that has to be reused. That is the only way out, or else you need to use it for other valuable production. Could you give real world industrial examples of where pre-treatment drastically improves recycling efficiency? Well, one of the most common scenarios that is very much evident in common knowledge now, that let's say there is trained recycling units versus untrained and unskilled recycling units. what happens is when we are looking at an unskilled recycling unit, the pre-treatment that we see isn't usually present. Let's say they are unskilled recyclers, and a group is sort of trying to recycle waste printed circuit boards, or they are trying to recycle some screens or computers. What they do, they would just remove some parts that could be reusable, and then the most if somebody has given them the idea that okay fine it could have some metallic components, and they just put it inside a small makeshift smelter, and then they'll try to recover some metallic values out of it. What that does is it can lead to carcinogenic gases generation because it's not pre-treated. So you haven't really thought of removing hazardous components from your raw material. You just remove what could be removed and put it inside us that makeshift smelter or melting unit or remelting unit, because pyrometallurgical units, smaller units, are most common methods by which these recyclings happen. Now, if things like this are carried out, the generation of carcinogenic gases is more evident. It's so much common. Now, what happens if you are trying to do this after you really do your pre-treatment? Now you have good idea about the process. Let's say the group is now well informed about what they're supposed to do and how to handle different types of e-waste or metallurgical waste or whatever they are trying to recycle. And they do the essential pre-treatment. Let's say crushing, grinding, sorting, they are doing delamination or whatever, and they are specifically performing the let's say recycling after pre-treatment. You'd see that the recovery of metallic values is high first. Second, it's lot more environment friendly, less hazardous, lot more environment friendly, and the overall impact on environment is very less. Adverse impact I'm talking of. So adverse impacts are very less. That really helps us to pinpoint the idea of, let's say, how pre-treatment really helps. Pre-treatment really helps in removing unwanted raw materials to interfere in our main raw material, something that we are wanting to target. That right now I'm claiming as main raw material. So if you want to, let's recover copper, for instance, and you have so many different materials inside alongside copper, and they are not just metals. Let's say they have glass fibers, you've got ceramics, you've got polymers. So how does it really affect your metal recovery? It affects by changing the chemical composition of the raw material itself. Now we can't really just put the whole raw material into a furnace and just set it off for smelting. It doesn't really help because everything else would get smelted, and first it would consume a lot of energy, second it would consume a lot of other resources apart from electricity, and third it would also cause lot of environmental damage because the slag would also be required to treat, and it's a lot more easier to just pre-process it and then recover copper directly. So in that sense, yes, pre-treatment really helps in improving the recycling. Now, the last question that we see here is aluminum dross recycling differs in terms of energy requirements compared to aluminum scrap recycling. How? So let us first try to understand that aluminum dross is a different waste and scraps are different wastes. And we have been discussing about scraps in this interaction, and we know that scraps, the most common go-to method is pyrometallurgy. So you take a scrap, you put it, you of course do the pre-treatment cleaning and all that, and then of course you might want to check the composition of the scrap. That would be very much beneficial. And then you just put it inside the furnace for, let's say, refining, or if you want to do remelting and smelting. So all of these processes are very well defined. What we want to do is check the composition and perform pyrometallurgical processing. What we would get is the recycled aluminum. There are side products of pyrometallurgical process, which would be aluminum dross. Now, comparing scrap recycling with dross recycling would be something that we really cannot put really comparative statements, because scrap recycling essentially would require primarily to go into pyrometallurgical route and perform the activities. Very rarely would you find any scrap being treated through hydrometallurgy or hydroelectro, because the main challenge has always been to recover metallic values. That's a general opinion. At the same time, of course, for research purposes, that we can go into hydro and hydroelectro also. But at the same time, if you look at aluminum dross industrially is recycled through pyrometallurgy, and of course, white dross you take and put it in a, let's say, pyrometallurgical unit. It could be a rotating furnace. It could have different types of facilities to assist the recovery of metallic values, and then you recover the metallic value. Hydrometallurgy of aluminum dross is also being explored on an industrial scale. Of course, it is very well thoroughly studied in lab scales also. But this is somewhat different from recycling scraps. And when we try and compare energy requirements, so essentially scrap requirement is pyrometallurgical. You would require the energy to melt the scrap, to hold it at a particular temperature for, let's say, refining, if refining is required. You would also require some mechanism to treat the slag also, which would be dross again, or aluminum salt slags if you are adding salts. So that is a different ballgame. And aluminum dross recycling would, if we are looking at pyrometallurgy only, is somewhat very much similar to a conventional refining unit, wherein you are taking the dross and you are subjecting it to a rotating furnace, let's say, and providing heat. And then again, you might or might not add salt fluxes. So there are salt-free technologies, and there are rotary salt furnaces. These are the pyrometallurgical technologies for looking at aluminum dross, and then you can recover the metal. So in that sense, both of them are pyrometallurgical routes. Just that usually for scraps, we don't usually go into hydrometallurgy or hydroelectro. There is one common question that could we take a course on chip and chip packaging and recycling? So the course content usually is of this particular course is essentially based on the electronic waste, and we limit our studies to waste printed circuit boards and batteries. Of course, this could be an area of investigation and further teaching in the upcoming years. So that's all from our side. These are the questions that have been asked. If there are any more questions, then I'm really open.
Sir, excuse me, sir.
Yes.
Sir, can you take up that the chip recycling in the next upcoming term? That's
So this is what I've just said. This is not right now a part of this course, and when we will have better understanding of the chip recycling is basically what I'm assuming that you are wanting to look at PCBs. Is that correct, or is it something else?
Yes, sir. The same. And the silicon chips as well.
Silicon chips. So, silicon chips are, I mean, if you're looking at solar panels, is that correct?
Yes, sir. Solar panels and the central processing unit, the chip we have that COC, SOC.
So, we are discussing solar waste printed circuit boards, recycling, which will be discussed later in the course. It is already there. The solar panels is right now not the part of the course, so we won't be able to discuss more on that. Just that the chips, the motherboards, the chips would be a different route for it would require a different route of recycling altogether, because you'll be looking at electronic components, ECs, and the ECs would essentially would require further pre-treatment to remove the epoxy resins and then recover, let's say, the metallic values from it. So that is a general hint that I can give right now. That is somewhat similar for solar panels also. So if you are able to dismantle solar panels and recover something valuable from it, it's a good good raw material to begin with. But it's not a part of the course, so we are not really going there. Yes.
Hi, may I talk?
Yeah, please.
Hi, thank you. It's a suggestion, not a question actually, because I am not a specialized audience of this course. It would be great if you include some pictures or videos of this recycling and recovery of metal. It would be great for the non-specialized participants to understand, because I have to rely on this pictorial, what's a drawing representations to understand the process. It's not easy for me to always get a real picture example. So it would be great if you take this suggestion. Yeah, that is one thing. Another thing, yeah, I am just following Logesh, I think his question regarding solar panel recycling. So you already mentioned that it is not part of this course. And another one is the lithium-ion battery. Are you covering only batteries, or it's a lithium-ion battery? Like we get an idea
So,
how? Yeah.
batteries, essentially the categories of batteries and the internal segments of recycling. It's already been put up in the course template, so it is already there.
Yeah, so we start from like how do we open the battery pack, then how do we recover the, is it
Yeah,
like
of
that?
course, it is being discussed and since it's the recycling per se itself is a very advancing and ever advancing course. Not that it has to be really old school, but it is now coming up as a new area of teaching and learning. So advances are always there, well within in a span of few months. So some of the technologies that you might see are, let's say, well documented for the past few couple of years. And then the new advances that would be coming up, let's say, a couple of years back, 1 or 2 years back, these would be documented in the upcoming sessions, maybe, let's say, the other versions of this course that might come up in the future. So it might also have solar panels and other electronic based topics. Yes.
Okay, thank you. Another one is, do we have, are we covering recovery of precious metal like gold, platinum, or because so far what I understood is more common metal, or what to say,
No, right now
abundant.
this course is essentially on the metallurgical waste as well as electronic waste. And electronic waste right now one has to really cover base metals, because the agenda of this course was always to understand first base metals, because precious metals only would be recovered when we are very confident on base metals. And when we are having good grip on base metals, we should be then transitioning into, let's say, critical minerals, REEs, PGEs and the other sets of elements that are present in, let's say, different segments of wastes. So, in that sense, we can also have a digression into the area of, let's say, automobile catalysts and other wastes, the other waste streams that really give us different types of elements. Those parts are not covered. To really understand the overall essence of waste recycling from electronic waste, we've limited ourselves to waste printed circuit boards and batteries, case studies of waste printed circuit boards and batteries only. Because, well, this gives us very broad idea about how different types of unit operations and processes can be pulled into a holistic picture, and you are able to sort of draw out the metallic values from various waste streams. So the key point has always been to focus on base metals, because base metals, if we are able to deal with base metals but in a befitting manner, that would be a lot more beneficial in a longer term. Of course, precious metal is always something that attracts most of the learners and audiences in general, but base metal has always been the focus. So let's say batteries and WPCBs have always been the easy and more comfortable areas that give us a good picture of the understanding in general.
Okay, thank you. An additional question is, are our technologies matured enough to work on this precious metal, or still are we a little bit behind? I mean, I'm just curious, or I am not updated. I don't know.
Actually, I think there are differences in opinion actually. So some group of researchers might say we have matured. Some of them would not agree with them. So I'm not really the one who should be commenting on this. I personally think that there are always scope of improvement.
Okay. Thank you so much.
Thank you. Any more questions, please?
Sir, I have two questions. One relating to the exam, the other one is about the internship. Sir, do we need to remember the compositions for the exam? The compositions of the draws.
Generally speaking, you should have a general idea. It's not essentially to remember everything for because these data points have been collected from various sources, and of course you have the whole set of references for all of these data points. But there could be an example when you can have an outlier that may not fall within the data sets that has been discussed. So of course it is very much possible that you can have outliers always. And what was the other question?
The second one is, sir, are you going to give any offer any internship to the people whoever score 90 to 100? Like now the NPTEL has given for winter internship.
That I haven't really decided yet, so I cannot comment on that.
Yes, sir. That's what I want to know. There. Okay. Do we get the notifications for that or announcements?
I think you will get information about that from the NPTEL team.
Okay, sir.
So I think I will answer that query, sir.
Yeah.
Yes, sir. Lokesh, a form will be open, and you can check that form and fill your details over there, and we will get back to you.
When is that form going to open, sir?
Hopefully within a month.
Okay, sir. That like now the NPTEL has given a criterion like 90 to 100% should be there in the same criterion will be present for the same.
Yes.
Okay, sir.
But it also depends upon instructors' availability. So Once you clear that cutoff mark, you apply, and then we will see. We will check with the professor's availability, and then we will let you know.
Okay, sir.
Yeah,
you, sir.
thank you. Thank you. So just now one more student joined, Arish. Mr. Arish, do you have any query? Please feel free to ask.
If there are any questions, please ask.
So I just checked the YouTube. There are no queries. Maybe we will wait for 2-3 minutes and see, sir.
Okay.
Yes, sir. Thank you, sir. Sir, can we wind up if there are no queries?
Yes. If there are no further questions, then we can close.
Yeah, sure, sir. Thank you so much, sir, for this live session. It was very informative and helpful. Thanks to all the participants as well for joining and making the session interactive. We are closing the session now. Thank you all.
Thank you so much. Thank you so much.
Thank
Yes,
you.
thank you, sir.